What's up, everyone? Welcome back to Better Biomed. Today we're going to talk about flow sensors, medical flow sensors to be more specific, which are usually related only to medical gases. So, medical flow sensors, they have some really unique properties and they're normally very expensive. And that's because they got to be pretty precise. So let's go ahead and let's take a look at some of these medical flow sensors. We'll go through some of the various technologies. I know I'm missing some of these. It's okay, but we're going to at least go through the main technologies and the manufacturers that support those technologies. Let's do it. All right, guys, so these are some medical flow sensors. And believe it or not, all three of the flow sensors in this image, they use a pretty vastly different technology between them. Interestingly enough, all medical flow sensors, all flow sensors in general, are related to Bernoulli's principle. So anytime you have movement of gases or compressed gases, Bernoulli's principle is always going to apply. So this is a typical ventilation circuit. You see over here we have a expiratory and you have an inspiratory, which means this is where you inhale and this is where you exhale. So as you inhale, it comes over here, you get fresh gases mixed with some recirculated gases, and it squeezes it to a certain quantity, it goes into the patient, and then the patient's own elasticity will exhale, and it comes over here to another one-way valve and out the machine. The reason I'm showing you this is because you want to keep track of how much gas is going to the patient and away from the patient, because you could cause some pretty bad health problems, or you could have a leak and you don't even know it. And your flow sensors, they're so specific that they can show that leak, and your machine will often alarm because of that. So here we go. That is a typical ventilation circuit. Now over here, right by the inspiratory and expiratory valves, this is where you'd find your flow meters. And interestingly enough, you can't see flow meters in this little diagram. Super wrong. Should be right about here and right over there. All right, so let's go through the main technologies behind flow sensors. The first one we're going to talk about is called differential pressure flow sensors. There's all sorts of different types of differential pressure flow sensors. The reason they call them that is because there's always some sort of occlusion in the middle, and they measure the difference of pressure between one side and the other. Now, as we already said, Bernoulli's principle applies to all of these, and that means that as gases speed up, they create a lower pressure zone. So what you do is you create an orifice, and on one side you're going to have pressure built up, and on the other side, as the gases go by, it creates almost like a venturi, and that creates suction, or a very low pressure zone right here. So on this side here, you're going to see the scale go this way, and this one over here, you're going to see pressure build up on this side. The higher the flow, the greater this differential is going to be. This is a fixed orifice flow sensor. Now this type of flow sensor is perfectly fine if you have a very specific flow rate that you're going to work with. Unfortunately, with medical applications, you're going to have pediatric patients, you're going to have geriatric, you're going to have, obese patients, you're going to have large patients, small patients, male and female, old, young. They're all going to take different ventilation settings, which means they're going to have a different pressure and they're going to have a different flow rate. So a fixed orifice, it's good for some applications, but for many patient applications, you're going to see that they're going to have something called a variable orifice. So right here we have a differential pressure transducer, and so it takes an analog signal, which is the pressure on each side of the orifice, and it goes up into a comparator circuit, and then it outputs a digital signal back to the computer, and the computer then comes up with whatever the calibration values are for that fixed orifice. And that gives you a pretty specific value. Now here is another example of a fixed orifice. Now, if you notice in the middle, there's a curved surface. It's kind of like an airplane wing, but upside down. The whole reason that an airplane flies is because the wing is curved and it creates a faster moving flow over top. And the faster moving flow is a decrease in pressure, which creates lift. So there's a decreased pressure because of an increase of flow rate, because of the flow restriction or because of the curved surface. So that's exactly what they're doing here. The pressure would come in on the left side. It would go across this flow restriction, which is also a curved surface, and it creates a low pressure side over here. So the faster the flow through here, the bigger the differential is going to be between one side of the flow restriction and the other side. And that is pretty much it for a fixed orifice. Now let's get on to the more complex type of flow sensors. This is the flapper style or variable orifice. Now here in the middle, you're going to have a mylar that is just dangling. So it now has a movable part. The other ones, there's no movable parts. That means that these ones here are much more durable. However, these ones here do not do so well with a varied amounts of flow rates. One consistent flow rate, no problem. Now on these ones here, the variable flow rates, you could have a low flow for, let's say, a pediatric patient, or you could have a high flow. Now what it's going to do is it's going to come through and it's going to lift the flapper just so, and that creates a little gap down here. So a low flow, the flapper comes down and it's almost closed, so it still creates quite the bit of difference on one side or the other. And as the flow rate increases, the flapper is going to lift and it's still going to maintain that difference of pressure from one side to the other. So that would be a variable orifice or flapper style flow sensor. Now these ones get damaged all the time from people sticking things inside, and it damages that mylar. If that mylar is damaged whatsoever, then it's done. That whole flow sensor is garbage. Now let's move to a Laminer Flow style flow sensor. Now what they do is they have a series of tubulars right here in the middle, which makes airflow linear, which is why it's Laminer Flow. On one side you're going to have a pressure measurement, and on the other side you're going to have a pressure measurement, because now you have a difference. As flow increases, it's going to get restricted because flow is normally turbulent. And since it's now going through a comb to straighten it out and make the air laminar, it's going to create a restriction, and that restriction is going to mean that there's now a difference of pressure. Now, interestingly enough, look here in the middle how it says that there's a heater. It has a heater because anytime you have small surfaces, you have the ability for water to condensate. So you have the heater, which keeps water from condensating, and that way there you can use these type of technologies. Without the heater, this type of technology would be miserable because it's going to start to occlude more and more as moisture builds up. Differential pressure with offset flow. Offset flow also uses Bernoulli's principle. Interestingly enough, there's a taper between the two sections of the tube, and that turbulent airflow in the middle actually creates the obstruction. Now normally this type of flow sensor, there's no moving parts, which makes it extremely reliable. However, they had a problem with moisture. So what they did is they created little grooves in the roof of the curvature, and those grooves help dissuade moisture from condensating and building up into large droplets. The large droplets could occlude your pressure tubulars right here, and that would create incorrect readings. Hot wire anemometer flow sensors. This is a style that's used by dragger pretty commonly. It requires a heating element, which you can see right here on these two prongs. It heats up, and as gas flows by that heating element, the faster the gas, the more that heating element cools off. Now this type of flow sensor does particularly well when it comes to moisture because you're heating something up, so obviously water isn't going to want to condensate in that region. However, this little tiny filament is kind of like a light bulb filament, and it can and will eventually break. It has a life expectancy. Now this type of flow sensor is being monitored with a voltmeter, and there's a little galvanometer right down here, and there's a known voltage source and a rheostat. All that takes place on a single circuit board for the dragger specifically. However, these are also some of the most reliable flow sensors, oddly enough, because they're very, very accurate when it comes to the quantity of flow, And because they're not inhibited by moisture, that means that they're applicable in a wide range, whereas some of the other ones, like even flapper ones, tend to have some sort of condensation buildup over time. Now let's move into some technologies that aren't that common. Now this is an older style one. I do believe that this one here is a GE, and the way this one works is the air comes in, it goes across a spiral grid, and these vanes create turbulence, which then creates a conical airflow, and that spins a rotating vane, and that rotating vane is what's measuring the amount of airflow. Now this one here has moving parts. Notice many of these flow sensors do not utilize moving parts because moving parts equal problems. They always equal problems. So that's why flow sensors that require no moving parts are better. Now this one here also has to deal with condensation, because when you have moving parts, any type of condensation can and will slow down this rotary vane. Also, as you increase the flow, the more that this type of stationary vane channel right here is going to be functional. At really, really low flows, you're not going to get so much of a vortex right here, so it's not going to work as well for a wider range of flows. So guys, that was just a quick breakdown on flow sensors. I know, it's just one of those things. It's because somebody asked me a question about it the other day, and I know of the major brands, but I didn't have any physical examples. Flow sensors can be very expensive. They can cost hundreds of dollars. So if I had those examples, I'd love to take them apart and show you piece by piece what the technology is and how it works. However, due to budget constraints on this channel, we cannot provide physical examples, so I hope the pictures and the diagrams do it for you. Anyway, guys, that is medical flow sensors in a nutshell. Hope you enjoy this. Thanks for watching.